Let's go back to making pizza. So there's our recipe again. And now we're looking at what we've got. We have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce. How many pizzas can we make? Quick, what's the answer?
3.
Somebody says 3. Could be right. I think it is. How would we figure that out? What's the thought process? You got the right answer. Do you want to tell me?
You divide everything by the amount that you're given, and the least amount is how many pieces.
Right. So she's taking each of these amounts and dividing by the number that you need. So 4 divided by 1. You could make 4 pizzas if you had enough of everything else. And 10 cups of cheese, we already did that one. 10 divided by 2, you could make 5 pizzas. 15 ounces of tomato sauce, you need 5 ounces for each pizza. So you take 15 and you divide by 5, you get 3. So when you make 3 pizzas, you've run out of tomato sauce, you can't make any more pizzas. Does that thought process make sense? Yeah, it's a limiting reactant. So I'm going to write it out. I know it seems silly, but it's helpful to write stuff out that we understand, because next we're going to do something that maybe you don't understand. So what I'm doing is I'm taking each amount, so 4 crusts, 10 cups of cheese, 5 ounces of sauce, and I'm going to figure out how many pizzas can I make. So pizzas per crust, it's 1 pizza from 1 crust. And so that gives me 4 pizzas. And for the cheese, we already did that one. It's 1 pizza for 2 cups of cheese. So we could make 5 pizzas. And for the sauce, you get 1 pizza for every 5 ounces of sauce.
15 ounces.
Thank you. We're starting with 15 ounces, not 5 ounces. That's important. So then this gives us 3 pizzas. Now what students sometimes do when we apply this to chemical equations is that they'll tell me that you could make 12 pizzas. Can I make 12 pizzas? No. I can't add these together. Yeah, from the 4 crusts I could make 4 pizzas, but I'm going to use cheese and sauce, right? From this amount of cheese, I can make 5 pizzas only if I have enough cheese and sauce and crusts, okay? So you don't take all of these and add them up. You take these and you say, which one is the smallest? Well, 3. So that's the answer to how much you can make. Because when you make 3 pizzas, you've used up all your sauce. Yeah, you have another crust left, and you've got some cheese left, but the pizza won't pass inspection if you don't have sauce. And we can't substitute ketchup or something. It doesn't work in chemical reactions. And it doesn't work at the pizza place either. If you've ever worked at a pizza place, they're not going to be happy with you if you start substituting things. Any questions? So here's this in pictures. 4 crusts would make 4 pizzas. 10 cups of cheese would make 5 pizzas. 15 ounces of tomato sauce would make 3 pizzas. We call the tomato sauce the limiting reactant because it limits how much product we can make. It's the ingredient that limits production. So in a chemical equation, the limiting reactant is the one that runs out, that limits the production of the product. So the tomato sauce is the limiting reactant. The number of pizzas that we could make is called the theoretical yield. So if you had that list of ingredients, those amounts, in theory you could make 3 pizzas. Now, I don't know about you, but when we make pizza at home, sometimes things happen. In the summer, we like to do the crusts on the grill, and sometimes we get distracted and we burn them, right? And so, you're doing them in shifts and you burn one. So we didn't actually make all three because one of them got messed up. And that happens in chemical reactions too. You don't always get the theoretical yield, but it's important to understand these terms. Limiting reactant limits how much product you can make. The theoretical yield is, in theory, if everything works out perfectly and you use up all of that limiting reactant, how much could you make? So just like when you're making something from a recipe at home, it's really unusual to have just the right amount of ingredients, right? If you were going to make a pizza, and you had a hard day, so you're not making the crust from scratch. You're just going to buy one of those pre-made crusts. And you're going to buy some tomato sauce, some pizza sauce, and you're going to buy some cheese. You're probably not going to be able to buy just the right amount of pizza sauce and just the right amount of cheese for the number of crusts that you have. And so there's always going to be something left over, right? In chemical reactions, that's how it is too. It's very unusual for us to have just the right amount of each ingredient. It's really not necessary, and it's just way too much work. So that often happens in a chemical reaction. The limiting reactant is the one that gets completely used up. And then there's some that are left over. There's excess of them, and so those are called the excess reactants. The actual number that you get is called the actual yield. We're not trying to be cryptic here. The theoretical yield, in theory, how much could you get? Everything works perfectly. In my experience, things rarely work perfectly. Actual yield is how much you actually get. You might burn a pizza, drop one on the floor, cat jumps on the table, and starts eating it, whatever. So that's the actual yield. A useful relationship is the percent yield. Remember, percent is the part divided by the whole times 100%. So percent yield is how much you actually got divided how much you theoretically could have gotten times 100. So if you had 100% yield, that means things worked perfectly. If you had, 75% yield, depending on what you're doing, that might be pretty good. If you had 2% yield, means things suck, right? Things are not going well. So percent yield is a measure of how efficient is the process. So there's a summary. That's a nice slide to look back on when you're not sure what these different things are. But I already covered all of that. So let's apply these concepts to a chemical reaction. We looked at this guy when we learned about balancing equations. 1 methane to 2 oxygens gives 1 CO2 and 2 H2Os. So that's what this equation is telling us. 1 CH4 is going to react with 2 oxygens. Well, what if we have 5 molecules of methane and 8 molecules of oxygen? Which one's going to get used up first? Well, here we've got a picture, so we can kind of, do it in sort of a cheaty kind of way. It's like, well, one of these is going to need 2 of those, right? And another one is going to need 2 of those. And then what do we have? Well, we've got 3 of these and 1 of those, and that's not going to work, right? Oh, I was looking at O2. Okay, rewind. Okay. I was looking at O2. So I should really read my own slide. Okay. I could edit that part out, but that's too tedious, so we'll just let it stand. Hopefully I won't do it again tomorrow. So if we have 5 methane molecules and we have plenty of oxygen, we could make 5 CO2 molecules, right? Here we see we have 5 carbons and there's 5 carbons in there, and presuming there's plenty of oxygen. We can show this mathematically: 5 molecules of CH4 times 1 CO2 molecule per 1 CH4 molecule, making 5 CO2 molecules. Same thing that we did with the crusts of the pizza, right? Then the 8 oxygen molecules. Well, 8 oxygen molecules, it takes 2 of these to make 1 CO2. And so 8 oxygens times 1 CO2 for every 2 oxygens gives us 4 CO2 molecules. So then what we do is we look, which is smaller, 4 or 5? 4 is smaller. This is smaller. So when we get to making 4 molecules of CO2, that means we've used up all the oxygen. The reaction stops. Just like pizza production stops when you run out of sauce. So the oxygen is the limiting reactant, and the least amount of product is the theoretical yield for CO2 molecules. Any questions? The train has a question. I don't answer train questions. Sorry, guy. Okay. That's looking at individual molecules. But usually we've got masses of products, and we want to know the mass of the reactant that's going to be formed. So this is the overall idea. We're going to take mass of A to moles of A to moles of P. So grams to moles, how many moles of product? Grams of B to moles of product. And then ask which is smaller, and take the smaller amount of moles of product and find the mass of product, and that's your theoretical yield. That's the way your book does it. There's nothing wrong with it, except that I think students tend to find it confusing. And so the method I'm going to use, we're just going to go grams to moles to grams, grams to moles to grams, pick the smaller, you're done. I think that's more straightforward, okay? Maybe not as elegant, but I don't think anybody really cares about how elegant their solutions are. Let's do an example. Ammonia can be synthesized by this reaction. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So again, we're using the chemical equation to organize the information. So let's see, 5.22 kilograms of hydrogen. And 31.5, actually I'm going to do it this way. I have colors, I'm going to use them. 31.5 kilograms of nitrogen, and then what are we trying to find? Theoretical yield of ammonia in kilograms. So how many kilograms of ammonia? So we have 2 reactants that we're given information about, and so we're going to do 2 calculations. Grams to moles to grams, or in this case, kilograms. So on this one, I'm going to show you that shortcut of semi-ignoring the kilograms. So I'll start here, 5.22 kilograms of nitrogen. And what I want to do is I'm just going to mentally separate the kilo and just let it sit there. So I'm ignoring the kilo, and I'm going to go from grams of nitrogen to moles of nitrogen. In the denominator, I'll have grams of nitrogen, and the grams of nitrogen will cancel out. Yeah, that's hydrogen. Thank you. That would have been awkward. Not that it isn't awkward now, but it'd be worse. Okay, hydrogen, hydrogen, hydrogen. Okay. Moles of hydrogen to moles of ammonia, and then moles of hydrogen come down here. So those cancel out. And then I'm going to go to grams of NH3 and moles of NH3 down there. So let's look at the units here. So what I've done is I canceled grams of H2. I left the kilo sitting there. Kilo just multiplies something by 1,000. So I left it sitting there. And so when I do this whole thing, I've got kilo, cancel, 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 grams. Okay, so the kilo didn't cancel out, and so the unit I end up with at the end is kilograms. Okay, so we need some numbers in here. Molar mass of ammonia is 17.043, and molar mass of hydrogen is 2.016. And then the mole ratio, 3 moles of hydrogen, so 3 in the bottom, 2 moles of ammonia, 2 on the top. And this should have 3 sig figs. So this is going to be 29.4, write down a couple extras, kilograms of NH3. And that kilo is just that kilo at the beginning that I didn't cancel out. Any questions? Now we're going to do almost the same thing with the other one, the nitrogen. So 31.5. kilograms. Okay, there's multiple ways to do this, and I don't want to confuse you with the whole kilogram thing, but I'd like you to be able to see what's going on. So another thing you can do here, in this situation, this is not the best, but another thing you can do with a number like 31.5 kilograms is instead of writing kilograms, you can write what kilo means times 10 to the third grams. So you can just put the meaning of the prefix in there instead of the prefix, and that saves you a step. This isn't actually going to help us much in this problem because we have to go back to kilograms at the end. So I'm not going to do that. Do you want me to do the shorter thing that I did up here, or do you want me to do the longer one showing the conversions at both ends? Shorter's fine? Okay. Whew. I didn't want to do that, but I would have because it's my job. Okay, now this is now this is kilograms of N2. So moles of N2 to grams of N2. The grams cancel, the kilo didn't get canceled. Moles of N2 to moles of NH3. I get moles of N2 in the denominator. Those cancel out. And then I get grams of NH3 on top and moles of NH3 on the bottom. The last term here is the same. I don't have to calculate anything new. And that's part of why I think it's best to just go all the way to grams. There's less thinking involved. 17.043. That's the same as the other calculation. Mole ratio, 2 moles of NH3 to 1 mole of nitrogen. And then we need the molar mass of nitrogen, which is 28.02. 2 times the mass of nitrogen. So 31.5 divided by 28.02 times 2 times 17.034. Again, three significant figures, 38.3, carry a couple extras, and the unit is kilograms of NH3. Because I didn't cancel this kilo. And I've got gram left, all the other units canceled out. So, how much ammonia can I make? 29.4, the smaller one. So the answer is the smaller one. There will be worksheets and labs where you have to write stuff like this out, and maybe on an exam as well. And one unfortunate thing that happens sometimes is that students get this far and they don't do anything else. And I can't give you full credit for that because you have to pick an answer. You have to pick an answer. So you have to indicate what your answer is. A box around it is good enough for me. Or, write 29.4 is the kilograms is the theoretical yield of ammonia. You have to indicate it somehow. The problem here didn't ask this, but what's the limiting reactant? It's the hydrogen. So we found the smallest amount of product, and to find the limiting reactant, you just trace back to what started that one. It's the hydrogen. Hydrogen is the limiting reactant. That tells us that there's nitrogen left over after the reaction is completed. And we could calculate how much is left over, but we don't want to right now. Mining companies use this reaction to obtain iron from iron ore. So they take iron 3 oxide and they heat it with carbon monoxide, and that gives them elemental iron and carbon dioxide. So the reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron. Determine the limiting reactant, the theoretical yield, and the percent yield. Okay, we're going to have 3 answers. Again, use the chemical equation to help organize the information. 167 grams of Fe2O3. Okay, 167 grams. And 85.8 grams of carbon monoxide. And then it says it produces 72.3 grams of iron. Determine the limiting reactant. Okay, to find a limiting reactant, we need to do 2 calculations and then look at the smaller amount of product, right? So we can't do limiting reactant first. Theoretical yield. You find the theoretical yield in the process of identifying the limiting reactant. Is 72.3 grams the theoretical yield? It's the actual yield. It says this reaction produces this. That's how much was actually made. We have to calculate the theoretical yield. So this is the actual yield. And we need to calculate grams of iron. So grams to moles to moles to grams. I'm going to start with the first one because that's what I like to do. 167 grams of Fe2O3. Grams to moles to moles to grams. 2 moles of Fe2O3. 2 moles of iron. 2 grams of iron. So we get the grams of Fe2O3 down there. This is very repetitive, the process. But what's beautiful about it is you learn the process and you can solve like a gazillion different problems with it. It's very useful. That's one of the things I like about math, is you learn a process and you can apply it to all kinds of different things, as opposed to like, memorizing parts of a cell. Well, you memorize the parts of a cell, but that doesn't do you much good over here. Well, what do we need in here? Molar mass of iron is easy, 55.85. It's an element. It's just the number under it on the periodic table. Mole ratio. We get 2 moles of iron for every 1 mole of the oxide. And then we need the molar mass of Fe2O3. So down here, Fe2O3. It's 2 times the mass of iron plus 3 times the mass of oxygen. 2 times 55.85 plus 3 times 16 equals 303.85. If I make a mistake, just yell at me. Or call out loudly if you don't like to yell. 1 mole to 303.85 grams. Okay, so math now. 167 divided by 303.85 times 2 times 55.85 equals, and our final answer would have 3 sig figs, so 61 point, there's 3 sig figs, write down 2 extras, grams of iron. Any questions? Now we do it again with the carbon monoxide. So 85.8 grams of CO. Yes? You got something else? What'd you get? Pardon me? Okay, let me see what I did wrong here. 167. Oh, is it the Fe2O3 that's wrong?
Yeah, that's fine. Yeah, 159.
Yeah, I don't know what I did there. Oh, I had some, yeah. I had some other number in my calculator, and so that didn't work out very well. 2 times 55.85 plus 3 times 16. Yeah, 159. Thank you. So get rid of that. $159.7. And then we gotta get rid of this. 159.7. And we gotta do that again. So I'm getting 116.81. Is that better? Okay, thank you. Okay. Back to our second calculation. So grams to moles to moles to grams. Grams of CO to moles of CO to moles of iron to grams of iron. We're going to have moles of iron down here, and we're going to have moles of CO. Make sure that O is a capital O, because it's not cobalt, it's carbon monoxide, and they weigh significantly different. So carbon monoxide, CO 12.01 plus 16, 28.01. I should write that in. And the ratio, 2 moles of iron to 3 moles of CO. And the molar mass of iron is the same, 55.85. $85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals 114.05 grams of iron. So how much iron could we get in theory? 114. So that's the theoretical yield. I call him Theo. His given name's too long. There's our theoretical yield. Rounded, that would be 114 grams. What's the limiting reactant? Carbon monoxide. That didn't go very well. Often called LR, limiting reactant. For me, that's good enough. You're showing me this is the limiting reactant right there. You could write it out in a sentence. I'm cool with that too. But you have to indicate it somehow. Because I want to know that you know which one it is. I already know because I've got the answers. The percent yield. So percent yield, we have to use an equation. Percent yield is what? Actual over theoretical. Times 100. Sometimes students forget to multiply by the 100. So then your percentages come out, well, 100 times too small. So our actual yield was 72.3 grams. And our theoretical yield, I want to use the unrounded one here. And that's got 3 sig figs times 100%. The units cancel out because they're the same. So 72.3 divided by 114.05. That's a mass ratio. And then I multiply by 100%. Do not use the percent key on your calculator. And I get 63.393%. 3 sig figs. I'm going to report the theoretical yield is 63.4%. Any questions? So if you are a mining company and you're looking at your yield of 63.4%, you're going to look and see, well, is there something we could do to our process here that would increase our percent yield? Because then we're going to make more money. So that's how you do those.